Hello everyone. In this particular video, we are going to understand how the frequency response function analysis will be done on a 2D plate using Abaqus software. I am going to take an example of a 2D plate is having a 2 mm thickness and its width is 200 mm and its length is 500 mm and a force concentrated force, or we can say the point load of 1000 Newton is applied at other end at the center. Okay, and the left end is fixed with a wall. Okay, and we are going to see why what is the frequency response function, FRF. It is a function used to quantify the response of a system to an excitation. We are going to excite the system with a force, but before that we have to understand what will be the natural frequencies of the system without any excitation. So we have to find out its natural frequency, omega n. Okay, so this excitation will be normalized by the magnitude of this excitation in the frequency domain, and we will see the various natural frequencies, and then we will define this system in a particular domain of these natural frequencies. Okay, for that I'm going to take a example of a material as a steel, and Young's modulus of this steel is 210 gigapascal, and in Abaqus these to be put in a size format means 210 and E9. Okay, in Abaqus E stands for 10, and if you write 9 just after E, then it means 10 to the power 9. Then the Poisson's ratio is the unitless quantity, so it is 0.3, and the density is 7850 kg per meter cube. So you have to take care about the units in the Abaqus. Okay, so in Abaqus we are going to only use SI units. Okay, there are several set of the units, different types of units you can use, but I'm going to take SI units. Okay, so this is the particular problem, and we are going to solve this using Abaqus. Okay, so in this workspace, we can see that there are modules, part, property, assembly, step, interaction, load, mesh, optimization, job, visualization, and sketching. And we'll see what modules we are going to use. Not all, but so many. So I'm going to make the part means this 2D plate. This 2D plate we have to make. So first of all, we are going to do create part. Okay. So part we are going. I'm going to write the name of the part. It is a 2D plate. 2D plate. Then this is the 3D kind of plate. There is a thickness also there. So this that thickness is going to be taken, but the overall this plate can be treated as a 2D plate, but Abaqus will treat as it as 3D because there are thickness. Okay, so 3D plate, 3D body it is, and it is a deformable because the every atoms or every particle of that uh, plate is going to be vibrate. Okay, so it will be deformable. Every material, every atoms are going to be displaced from their original position, so it should be deformable. Then it is a solid, or we can say it is shell. So we are going to make it using planar. Okay, so we have to give its thickness also. So we are going to use a planar and shell. Okay, and the workspace is about we can see that its maximum size is about zero point 0.5 meter. So I'm going to take the size of the workspace as a 1 meter. Okay, then continue. The name must be it should be alphabetical, so it is 2D. Continue. Then I'm going to make that plate using rectangle command. what is the first point of that? Pick a starting corner for the rectangle. I'm going to take it as a origin 0 comma 0. Then we have to give this opposites corner. The opposite corner is of we can see that it is zero point 0.5 meter from here. It is 0.5 meter, and then height is 0.2 meter, right? Then point we have to take zero point 0.5 comma zero point 0.2. Okay, then enter. As we can see that a rectangle has been formed here. Okay, it is not formed, I think. So 0, then 0 0.5 comma 0 0.2. Oh, two rectangles has been created, so I have to cancel this. It was very big, so I was confused that where it is. So I'm going to create for once again 2D plate, then 3D deformable shell and planar 1 meter, and rectangle I'm going to take 0 comma 0, then 0 0.5 comma 0 0.2. It has been formed. You can see this has been formed. Dismiss, done. You can see that the plate has been created. Then we have to define the property of the material. Create material, then write the name of the material. It is steel. In general properties there is density, and density is 7850 kg per meter cube. So 7850 kg per meter cube. Then directly go to the mechanical elasticity and put the elastic properties. So 210 E9. E9 means 10 to the power 9. 10 to the power 9 means gigapascal. Okay, and Poisson's ratio is 0.3 as we have seen in the PPT. Okay, so property has been assigned, but we have to create the section also. So we have to go and the next, the create section. Section is a you can say that it is a plate, and it is a shell we have defined during creating the part, and shell, and it is homogeneous. Then continue. Now I'm going to put the thickness of the plate. We haven't defined the thickness of that, so we have to give the shell thickness. What was it is 2 mm. So 2 mm means 0.002, and material is steel. We have created that is steel, and it is assigned, and then okay. Then section assignment we have to put assign section. Assign section, we have to select all the part, and that section will be assigned to this part. Okay, then done. Plate. Okay, okay. Then we have to go for the assembly. There is no there are no more than two parts, but we have to create an instance that we have only one instance, and it is independent because there is only one part, so it is a independent part. Okay, so we have to create instance, then okay, and then we have to go to the very important module, that is step. Then create a step, and this step is for modal analysis, right? Modal analysis is nothing but it is the analysis where we are going to find out all the natural frequencies of the system. So we are going to disturb the system, so we have to use linear perturbation, not general. Linear perturbation, and we are going to find out the frequencies, so we have to select this frequency, then continue. Okay, then continue, and we have to use Lankos for the better results, and then values, the number of eigenvalues. The Abaqus understand only the eigenvalues, not the natural frequency. So natural frequency is nothing but it is eigenvalues of the system after solving the differential equation of the system. Okay, so the we are going to find out the number ranges of the natural frequency, that is total 10 frequency we are going to find out. Okay, then okay, then we are going to do interaction. There is no other parts or other environment is going to interact with the part. So there is no, there should not be used interaction module for that, for this particular analysis. So we go to directly load. Okay, so load, we are going to apply only boundary condition in the modal analysis, because we are not going to apply the force, because that force will be act as a forced vibration. So we are not going to apply that, because we are interested first to find out the natural frequency, and natural frequency is not depending upon the force applied. Okay, so we are going to apply only boundary condition on the system. As we can see that in this figure, in the fixed support is at the left side. Okay, so I'm going to rotate a little bit this system. Okay, so we can see the edges where we are going to use boundary condition. So this is the create load. So we are not going to first creating the load at the this point. So first we are going to create boundary condition. Boundary condition, it is left fixed. Okay, left fixed support, and it is encaster, completely fixed. Then continue, select the edge where we are going to apply the boundary condition, then done, and then we are going to select encaster where u1, u2, u3, all the translation, all the rotation should be 0. That means it is fixed. Okay, so the fixed support has been created here. Then we are going to create meshes. In the mesh, we are going to create seeds. How many, or we can say how, what is the size of that in this, what should be the size of elements. I'm going to apply 0.05. This is very larger size elements. So I'm going to reduce it a little bit. 0.025, it is also very less. I'm going to use 0.15. Let me check. It is also not so good. I'm going to use 0.010. I think it is better. No, I'm going to reduce it a little bit, 0.005. Apply. I think it is better. Okay, then okay. Then I'm going to create mesh. This is fine. Very fine mesh has been created on this 2D plate. As we can see that it is not looking, seems like a 3D plate, right? So if you want to check its 3D view, means its third dimension, that is thickness, we have to simply go to the viewport, view, and in view there is a image movie options. Sorry, assembly display options, render cell thickness, apply. Okay, now you can see the thickness of 2 mm. You can easily visualize it. Okay, so this thickness can be viewed, but I'm going to deselect this view option, because we are going to use only the middle surface of the system. Okay, the next part is job creation. We are not going to optimize the problem, and we directly go to the job, create job. Job is modal analysis. Just remember that in job you have to put the name without any space. So I'm going to use underscore. Then continue. Okay. Go to the job manager. Submit the inputs. Now the model is running. Wait for a minute. So the model has been run completed successfully. Okay, now we can see the result, deformed result. Now, okay, so this is in the first mode. I'm going to check its animated images. So you can see that there is 10 modes total, frame 1, 6, 7, 8, 9, 10. You can see that, and there are several frequencies are also there. So I'm going to see the result, step and frame. You can see its natural frequency from 6.8306, 335.72, 42.640, and so on, and the maximum it is the 10th mode frequency is 351.04 cycle per second. The first frequency is 6.8306, okay, in the model case analysis. So we haven't applied any force. The natural frequencies comes out as you can see. Okay, so we have gone through the results as like that. Okay, now we need to go for the frequency response function. We'll see in the next part, in the next video. Thank you.